So Dr. Doron Swade has studied physics, electrical engineering, philosophy of science, machine intelligence, and history at various universities, including Cambridge, University College London, and University of Cape Town. He has a PhD in the history of computing, and he's visiting professor at Portsmouth University and honorary research fellow at Royal Holloway University. Doron is an engineer, historian, and museum professional. He was senior curator of computing at the London Science Museum for 14 years and later assistant director and head of collections. And specifically, he's an internationally recognized authority on the life and work of Charles Babbage and the mastermind of the construction of Babbage's difference engine number 2, built to original 19th century designs. The engine, completed in 2002, weighs 5 tons and consists of 8,000 parts and is on display in the Science Museum. Doron.
Thank you very much, Andy. My brief this afternoon is to provide some historical context for EDSAC and its possible meanings. A few weeks ago, I thought that I would stress test how I would do this, and had the good fortune to speak to Professor Wilkes to run these ideas past him. After about 10 minutes of very patient listening, Maurice, with great kindness, urged me not to spend all my time philosophizing, unquote. There is no meaning in life, he said, even when it comes to computers. I will at times refer to Maurice, as Professor Wilkes, and as Wilkes, as is an academic convention. All these forms of address are used with affection and respect. The computer as an artifact, despite Maurice's urgings, remains something of a challenge to history. And my brief this afternoon was to reflect on this and where we could locate EDSAC in a landscape of interpretation. Obedient to Maurice's urging not to spend too much time philosophing, I will be mercifully brief. A famous logician memorably opened a presentation by saying, "Before I speak, I'd like to say a few words." So before we look at historical perspectives, I'd like to just perhaps produce a thumbnail history of Maurice and the history of the EDSAC project. The jumping off point was the now famous Moore School lectures. They were held in Philadelphia by the ENIAC and EDVAC team between 8th of July and 31st of August 1946. The ENIAC, designed and built by Eckert and Maukli, was an 18,000 vacuum tube monster of a machine built during the war to compute firing tables. Though technically a calculator, ENIAC is the object that symbolized the start of viable electronic computation. The Moore School lectures were intended to disseminate wartime experience, and out of the blue, Maurice received an invitation to attend. Maurice had, by that stage, already read Neumann's famous 1945, the draft report of the EDVAC. This is perhaps the seminal, perhaps the most influential document in the history of computing, in which von Neumann describes the essential logical features of a modern digital electronic computer and describes what has become known as the von Neumann architecture, which has dominated computer design from then till the present day. The paper, von Neumann's report, was given to Maurice by Leslie L.J. Comrie, and Maurice had it overnight only. Comrie was leaving the following day. With no mechanical means of duplicating this thing, Maurice had very little sleep that night. But by the time the Moore School lectures arrived, Maurice was already quite excited and not unfamiliar with the EDVAC, ENIAC, the wartime EDVAC, ENIAC developments. Because of the difficulty of getting a sea passage in the immediate post-war period, Maurice in fact missed the first month or several weeks of the course with no great damage done. It was covering material he was really familiar with. But once there, he spent time with Hermann Goldstein, with Presper Eckert, with Maukli, and visited Aiken, who was developing the Harvard Mark I in Boston. When Maurice got back to England in September 1946, he described himself, quote, as fully genned up. The benefits of the stored program were assumed. This was a legacy of the ENIAC EDVAC project. The stored program concept emerged from the ENIAC work and was embodied, if you like, in the von Neumann authored report, first draft report of the EDVAC. He was appointed director of the mathematical laboratory here in Cambridge on the 1st of October 1946 with a budget to be expended at his discretion. Having financial control meant that he could lead without bureaucratic interference. Leading without bureaucratic interference, Maurice has described as a very unusual circumstance. When I tasked him and said, how is it that you succeeded where others had succeeded less well, he said, well, they had committees to help them. So we have a sense of a very strong individual leadership and the extraordinary freedoms conferred to him by the directorship of the computer laboratory to actually do what needed to be done as he saw fit. And this is what I think Maurice means by these circumstances were very unusual. He put together a team, started development. He had already begun sketching the outline on his trip to Philadelphia and in fact on the transatlantic passage on the Queen Mary. So he was already ready to go and, as it were, to use an American colloquial, hit the ground running. And the machine was, of course, EDSAC, Electronic Delay Storage Automatic Calculator. This name was in overt homage to the American EDVAC. So there was a clear and overt indebtedness to the dissemination, the technology transfer that had occurred in the Moore School lectures. He developed the acoustic mercury delay line memory, as we've heard called tanks, using his wartime knowledge of radar to design the control circuits. David Wheeler joined the project in September 1948 and was to play a major role in software development. There were many pioneering developments. The use of subroutine libraries and the principles of microprogramming are two of very many. Maurice made a strategic decision to run the machine not at 1 meg, which was the limits of the technology of the time, but at 0.5 meg, a conservative decision. He says to this day he never regrets that. The purpose was to make the design more straightforward. The same lesson was learned by Seymour Crane, his design of the CDC 6600, where he deliberately chose in 1963 to use not the newly available chips, but discrete component transistors, a hugely successful and influential machine. Finally, and rather suddenly, Maurice recalls, on the 6th of May, 1949, 60 years ago today, to the day, the machine read a program tape for computing a table of squares and printed the results. The 3000 vacuum tube machine had taken under 3 years to design. This is an extraordinary achievement given wartime shortages and the novelty and pioneering nature of what was undertaken. EDSAC 1 gave consistently reliable computing service for just under a decade and was decommissioned in July of 1958. Work was transferred in the months before to EDSAC 2. In the interim, there was EDSAC 1.5, which was an experimental machine which explored the use of core store memory, which was at that stage quite relatively new. EDSAC 2 was decommissioned in November 1965, and this marked the end of a thoroughbred line of EDSAC spanning just under 2 decades from conception to close down. So we have just under 2 decades from the conception of EDSAC, with Maurice's return from the Moore School, unto the final closure of EDSAC. Of course, EDSAC lived on in the Leo, which was informed, the design of which was informed by the EDSAC expertise. Leo 1 only. Thank you, George. Not 3 weeks ago, Maurice confided that even today, quote, EDSAC stands up as an architecture. I'm proud of it. I think that says something for the quality of what went on at that time. So much for a thumbnail sketch of EDSAC and its project and its origins. Now to historical perspectives. If we look at the overall trajectory of computers, EDSAC stands at the very start of a distinct phase in computers. That is to say, it marks the emphatic emergence of computers from the laboratory to the workplace. That is to say, it emerged from the constituency of people, the priesthood of designers and practitioners who developed these machines, into a constituency of people that used it. So EDSAC, if you like, defined a new constituency of user. It made the user visible in a way that was quite unprecedented. The charmed circle of people who developed and designed these produced experimental machines. This was a machine which, as we've heard, specifically from the start was intended to provide a useful computing service. The ACE computer at the National Physics Laboratory, Leo, developed at Lyons, informed by the EDSAC design, and later the Ferranti Pegasus and Elliott 803, are examples of machines that emerged into the workplace during the 1950s and 60s. As part of the progression of computers, from sometimes temperamental experimental monsters, large thirsty machines with thousands of vacuum tubes that were perhaps more efficient at central heating than they were at computing, they emerged into the workplace to be used in a reliable way by people who were not necessarily engineering specialists in the technology. The title of the seminar, Inventing the User, was intended to capture this transition. My strapline for this whole area for many, many years has been, Wilkes invents the user. And when I suggested this to Maurice, he actually said, again with great patience and kindness, that perhaps the strapline was misleading. He didn't invent the user. He said the place was bursting with users. There were people waiting with needs, with computational needs that were ready to be fulfilled. But I still think the strapline does some good work. It identifies a constituency of practitioner which had not been identified before, and it became the terms in which the utility of computers after that were judged. To what extent did it have utility for doing real work? And EDSAC, if you like, marks that fundamental progression from experimental machine, from tinkering engineers into the workplace. We've heard that EDSAC was the first usable electronic stored program computer. We've said something about users. The stored program. The stored program concept is routinely cited as the defining feature of the modern digital computer, the feature that marks the essential transition from calculator to computer. There are countless accounts, both popular and scholarly, that attest this and assert the truth of this proposition, that the defining feature of the modern digital computer is the internal stored program. For many years, I assumed that the significance of the internal stored program must be self-evident, because nobody actually explained why it was important. I assumed there was some deficiency in my computer science training, or there was some blank that I had which did not make it self-evident. Why was it not obvious why the internal stored program was so important? Why was it the central plank by which we defined modern digital computing? After a few years, I became bold and began asking around. What was it about the stored program that actually gave it such a central role in defining this machine? What I did was I conducted a survey. I began to ask people. I asked computer pioneers, the first generation of programmers. I asked computer practitioners and leading computer historians. A totally open-ended question. What is the significance of the stored program computer? Those I consulted included Brian Randell, Donald Knuth, Bob Patrick, first generation UNIVAC programmer, Jack Copeland, published widely on Turing, Mike Mahoney, Princeton, historian of computing, Martin Campbell Kelly, perhaps the most preeminent UK history of computing, Bill Asprey in America, and a raft of Silicon Valley entrepreneurs to whom I had access to while working there recently for the last 2 years. What was intriguing about the answers that I got, that none of them were the same. The distinction between principle and practice was thoroughly blurred. Answers included engineering convenience, speed, since data and instructions were held undistinguishably in memory, the fact that you could apportion memory, the resources, the memory resource of the machine, towards data or towards instruction, depending on the needs of the problem. So it was a question of, if you like, engineering or computational efficiency. Other responses including the ability for a program to alter itself under program control. Donald Knuth, perhaps the supreme authority on programming, when I asked him, said that before the stored program, there was no clear idea of what a program was. In fact, the discipline of sequential memory defined the structure of what you meant by a program, that the word program and examples of programs up to that point, the word could not meaningfully be used until stored program, another very intriguing perception. In the context of the self-modifying properties of internal stored programs, I suggested perhaps in some quarters that the ability of a program to operate on another program as object created the possibility of assemblers, compilers, and interpreters, and that actually this, if you like, a secondary corollary of internal stored program was perhaps one of its major planks. This view was met again with indifference, and that's no reflection on the folk. Each person had a very extraordinary view that illuminated some different aspect of the stored program computer. There was no clear single answer on offer. There was also little consensus amongst even the separate constituencies, amongst historians, amongst programs, amongst computer pioneers, about what was going on. We can't go back to the inventor of the concept. There's no single originator of the stored program concept. There were many, many contributors, many individuals who contributed to the idea. The players, the events, and the machines are well known, and these are largely uncontentious. But the cross-influences between them remain quite elusive, and the claims and counterclaims have done nobody any credit. The disputes about primacy and priority, precedence and priority, actually still continue to divide the history computer community as to who originated what and who learned what from whom. In historical terms, the exercise is a bit suspect, because what we're trying to do is to resolve the significance of the question of the internal stored program by looking at the logical architectures or engineering convenience or engineering practice. Whereas what we should be doing is, in fact, looking at the key motives, the intentions of the understanding of the originators of the idea. How did they articulate the utility of the internal stored program? What were their perceptions at the time of what benefits this feature, this apparently defining feature, would confer? Nobody challenges the centrality and the use that the internal stored program does in defining modern digital computers. But it's quite irksome, that it's quite difficult to explain in simple terms why it is as significant as it is held to be. Perhaps we should not be too hard on ourselves, or perhaps we should not be surprised that computers, if you like, resist being absorbed into our assumptive worlds, placing it into the landscape of the familiar. This is written by Marvin Minsky, pioneer of artificial intelligence at MIT, in 1963, in his preface to his book Finite and Infinite Sets. Finite and Infinite Machines. What is it? Finite and Infinite Machines. He wrote, "Computer-like devices are utterly unlike anything which science has ever considered. We still lack the tools to fully analyze, synthesize, or even think about them. Neither history, nor philosophy, nor common sense will tell us how these machines will affect us, for they do not work as did the machines of the Industrial Revolution." This is a startling and quite shocking statement. What Minsky is arguing is that this is not just a difference in degree, this is a difference of kind, that computers as artifacts are logically and historically novel, that our normal categories of definition and our means of interpreting this actually do not apply. We have now a new phenomenon. What can we make of the idea that computers are unlike tools of the Industrial Revolution? What characterizes the tools of the Industrial Revolution for which computers are excluded or exempt? How do we locate computers in the landscape of the familiar if they are unlike, in some respects, what has gone before? If computers are a new category of object, then this poses questions for historians. Can we subsume the history of computing into existing history of technology that considers the development and fates of traditional devices of tools, machines, cars, trains, textile machines? Do computers demand or require distinct history? Do histories apply generically, or if a computer is a distinct artifact, does it demand some distinct treatment? Perhaps we're looking too hard. Is there, after all, a grand thesis of technological change? Computers are phenomenally successful as products. Is there something this tells us about technological change, history of technological development? Can history tell us more than stuff happens? Is there anything more that can be said? Perhaps there is no. Perhaps we're looking too hard. There is no explanation for this. Is history just a story without a plot about which we agonize pointlessly? And I go back to the thing that haunts me, which is Maurice's urging not to spend too much time in philosophy. What is the problem here? How do we identify, how do we absorb a computer into our assumptive worlds? What do we say it is like, what is unlike? So let's back off a bit and approach this differently. If we reflect on the development of electronic digital computers over the last 60 years, what is it that invites explanation? What is remarkable? What is the explanandum for an historical account? In what sense do computers stress, agitate, or irk us in giving an account of what they mean? There are at least two features which stand out, about which there appear to be violent agreement. The first is proliferation, that the computer is a remarkably successful product just in terms of the numbers of these things that exist, certainly in comparison to technologies that preceded it, cars, trains, their rate of growth. The second thing is the versatility, which I mean the plasticity of function, that is the ability, the ease with which its function can be changed. Now, the proliferation of computing, as we know, is partly underpinned by Moore's law, the remarkable consistency with which performance roughly doubles every 18 months for roughly the same cost. Moore's law has been the engine of the economics that allows complexity to be affordable to the extent of computing power being affordably incorporated into consumer items. The second feature I mentioned is versatility. In this respect, computers embody a paradox, plasticity and brittleness. On the one hand, computers are flexible, their function is easily changed. On the other hand, they're deeply brittle. One bit wrong, the system crashes. So again, is this like or unlike familiar objects to us? Computers embody other paradoxes. They are completely deterministic, and yet they are unpredictable, not because they're erratic, but because the complexity of their execution defies our ability to foresee outcome. So we have, again, something a bit like chaos theory. We have determinism and unpredictability, which in the past, certainly in classical terms, are two things which did not normally associate together. There is another paradox, and that is of rule-based creativity. But all that is an aside. I mentioned this only in the context of Minsky's claim about computers belonging to a new category of object, that we cannot assume that existing modes of thinking will exhaust their meanings. Versatility or plasticity of function, as we know, is underpinned by Turing universality. It's so taken for granted now that the specific function of a computer is determined by its software or its program, that it actually is very difficult to recover the sense in which this is remarkable. But the fact that of it being so is actually an Olympian accomplishment. The fact, actually, the general purpose notion of a computer, a standard, existing, assumed notion of that the function of a computer be changed by a program, is so banal, it's almost impossible to recover the sense that this is rather extraordinary. The ability that's formulated by the concept of Turing universality is what confers the general purpose versatility of the machine and accounts for the plasticity of function that is part of what underpins the remarkable phenomenon of computing machines. This is again a statement that appears banal, but one that will take more time to explore. So, in conclusion, we come back to the question of the significance of the stored program. The internal stored program that allows us to implement the internal stored program that allowed us to implement the universality that places the computer as a distinct category of artifact. It is the way specific function is embodied in and incorporated in the machine. Alan Bromley, an Australian computer scientist, identified 10 elements or steps that comprise the realization of the stored program concept. 2 of these he attributes to Wilkes and the EDSAC. So the stored program was not something given, just implemented in engineering terms by EDSAC. In fact, the seminal and influential developments of EDSAC, which influenced significant post-war developments, actually helped formulate and constitute actually what the stored program was. The first was instruction building, that is the use of loaders and assembler, that is jointly attributed to Wilkes and Wheeler. The second is hierarchies in machines in program in the use of microprogramming, and this he attributes to Wilkes alone. This is Bromley's analysis of this very complex idea, which accounts for why it is. There were so many different views of what its benefits were, and why each illuminates a different aspect. When you bundle them together, there are in fact 10 separate elements that make it significant, and this accounts for why there was this early confusion, or at least the variety of responses which people gained from different perspectives. So Wilkes and EDSAC made defining contributions to the realization of the stored program concept, which remains the defining feature of the modern digital computer. And finally, it was EDSAC that was the first practical implementation of a usable stored program machine. It was both the specific achievement of its design, its construction and use, and also a milestone in the larger movement that mushroomed into the developments and products that we marvel at